Welcome back, it's Mr. Tuxford here, and we're just continuing our step-by-step guide on the Level 3 Physics Investigation Standard. So far we have read the task, identified variables, written a method, explained accuracy techniques, constructed our raw data table in Excel, ensuring things are to the correct level of precision, copied it to our Word report, and of course made our non-linear graph and stated the relationship. So onwards, let's go. Making a processed data table. So, easiest way to do this is of course in Excel. So here's our raw data table from before, our graph, and now our processed data table. And in here, we will process our uncertainties, transform our independent variable so that we can plot the linearized graph. So that's what we're going to get up to in this video. Alright, our process data. Firstly, copy your independent variable, so length, Control C, Control V, as well as the uncertainty in that length. And we'll start, this step is kind of optional, but I strongly recommend it because we have uncertainties both in the length measurement and in the time period measurement. And so for NCEA Level 3, you technically only need one of those error bars, so one direction, but it is best practice to have both. So I'm going to show you both. So, can you guys hear that background noise? I hope not. Anyway, back to what we're doing. Uncertainty in length and length. Let's find the percentage uncertainty in length. So to do so, equals, you select the uncertainty, absolute uncertainty, you divide it by the measurement, and you times it by 100, right, 100%. Enter. So that's 0.5%. Yeah, like before, if we double click this green square in the right corner, it propagates down, and we should round it to something sensible. So percentage uncertainty, it's not as strict as absolute. Absolute uncertainty is 1SF. 1SF. So let's just go 2dp. Seems reasonable. So you click a cell, the number button at the top. There we go. Let's make those 2. Cool. Again, percentage uncertainty doesn't need to be to 1SF, but round it sensibly. Great. So we've processed an uncertainty. We do need that for a cheat. Next up, let's just tick off what we've done so far. Next up, we need to transform the independent variable. So this is the same as level 2, where we plotted our non-linear graph. We've identified that length needs to be square rooted, right? It's period proportional to square root of length. So our next step is to square root our length measurements. So you can go equals SQRT, right, square root, open bracket, select the length measurement, so click, close bracket, enter, and like before, to repeat that rule, but for the different lengths, you can click and drag, or double click this green square. Nice. And so in my heading, I've written square root length, and the units, it's a little bit finicky on Excel, but meters to the power of a half. In other words, that's the square root of meters. So we have transformed our independent variable. And just a note here, this example is a square root relationship, but if you were investigating a squared relationship, instead of equals square root, you would do equals, click the length, shift 6, so that's to the power of 2. Right, so that's squared. If you were doing an inverse relationship, you would do equals 1 divided by the length. And if you were doing an inverse square, you would do equals 1 divided by the length squared. 1 divided by, maybe use brackets here actually, the length squared, close bracket, like that. So it all depends on the task and your theoretical equation. Sweet. Up next, calculate the percentage uncertainty in the transformed independent variable. So whenever you transform a variable, whether that's square rooting it, squaring it, inverting it, or inverse squaring it, the percentage uncertainty also changes, along with its absolute uncertainty. But these calculations are a lot easier to do in terms of percentage uncertainty before then converting it to absolute uncertainty. So if you're a bit confused on this step, your SciPad has some good pages on that, I think like around 36, if I recall. So definitely have a look there as well. So let's calculate the percentage uncertainty in our transformed variable. In this case, since we've square rooted the length, the percentage uncertainty would be half of the percentage uncertainty in the length. So equals, select that percentage uncertainty, divide it by 2, and again, click the green dot, round them to something sensible, 2dp. And then for the absolute uncertainty, that's where we take the percent uncertainty, divide it by 100, right, to convert it to a decimal, and then we multiply it by the square root length value, like so. Enter, and then again, double click. You'll notice these are all 0.001, so let's just reveal a few more decimal places to make sure it's rounded correctly. Okay, so take away 1, take away another, okay, and then the top one we can take away 1 more. And again, absolute uncertainty is to one significant figure. Cool. So we worked out the percentage uncertainty for the square root. Right, we halved the percentage uncertainty for length because the square root length has half of the percentage uncertainty. Then we found the absolute uncertainty in square root of length and rounded it to one significant figure. Cool. All right, up next, we need to work out the uncertainty in the time period. So we've got the uncertainty in square root length. Now we need to focus on the vertical uncertainty, right, and time period. And there's two things we need to check. Firstly, using the half range rule, we can calculate the uncertainty through our measurements. And secondly, we can consider the uncertainty purely based off of like the precision of the equipment or our reaction time. And whichever one is greater will be the final uncertainty for that particular measurement. So let me just get the average for one period down. And you'll notice when I copy and pasted, these are completely different. That's because it copied the rule, right? The equals F3 over 10. So instead, you can paste just the values. And again, let's just round it down a little bit to start, like so. Oh, and again, missing seconds. So, half range rule. The half range rule is where you take the maximum measurement between your 3 trials, you subtract the smallest measurement, and you divide that answer by 2. In other words, from the average, what do you need to add to get the maximum value? What would you subtract to get the smallest value? And so the maximum, take away the smallest, divided by 2, gives you that uncertainty. You can do this by hand. So getting out your calculator, 9.4, take away 9.22, divided by 2. But we're in Excel, so I'll show you how to do it correctly. Yeah, with a formula. In fact, the formula is just this: maximum, take away minimum, divided by 2. So I'll show you how to write that formula. Equals, I start by opening and closing a bracket, dividing it by 2. And you might get an error, but just close that out. So in this bracket, we need the maximum, take away the minimum. So to dynamically get the maximum, you write max. However, max is a function, so it takes an input, and that input is these 3 cells. So it'll find the maximum between these 3 values, and then we subtract the minimum. Again, click, drag to select those 3 values, close the bracket, and here we have it. So equals, open bracket, maximum of those cells, take away minimum, close bracket, all divided by 2. And then we can hit enter. And it's always good to just check the first one with your calculator to make sure it is right. And then double click to drop down. And that is the uncertainty in time period based off of your measurements using the half range rule. Of course, we do need to round this to 1 sig fig. So there we go. And then these ones also to 1 sig fig. Oh, I have forgotten something. Did you catch the error? This was the uncertainty for 10 periods, wasn't it? Because these measurements were for 10 periods. And so, of course, for the uncertainty in 1 period, measured in seconds, it would be the uncertainty in 10 periods divided by 10. And again, let's round these to 1 sig fig, like so. Good thing I caught that. Or you, if you're yelling at your screen. So, just quick recap. Half range rule uses this formula. Maximum of your trials, take away minimum, all divided by 2. And in this case, we also divided it by 10 because this was for 10 periods. And finally, we rounded it to 1 sig fig. Awesome. Alright, and now the other way of getting this uncertainty in time period is through reaction time. Now, it does depend, right, on your reaction time, other conditions, but we'll just take reaction time to be about 0.3 seconds. And so if you measure 10 periods, divide it by 10, the uncertainty in 1 period would be 1/10 of 0.3 seconds. In other words, 0.03 seconds. And so now we need to compare which uncertainty is greater. Whichever one is greater is our final uncertainty. And in this case, it looks like the reaction time uncertainty is greater than every half range rule uncertainty. So these will be our final uncertainties. Cool, and so that is the absolute uncertainty. Now, for your report, you should copy this process data table or screenshot it. So let's just copy it in. Copy. Go back to Word. Right after the relationship, we have our processed data table. Zoom out. Make it smaller. Oh my goodness, this is quite quite a wide one. There we go. Cool. You could also screenshot it and like rotate it so it goes the lengthways of the page. That's fine too. So processed data. So length, uncertainty in length, percentage uncertainty in length, transformed variable, percentage uncertainty in transformed variable, absolute uncertainty in transformed variable, average time period, uncertainty by half range rule, and then by reaction time. And so under that, I strongly recommend you just type some examples. So like example calculations, or like I've done, you could put it in the top here. Yeah. All right. So with that, we will just finish off plotting the linearized graph, and then the next video we'll look at the error bars. Cool. So let's just zoom out. So the linearized graph, we select the transformed independent variable. So reminder that is square root of length. We hold control. We select the average, right, for one period. That was our measured variable. Like before, insert, charts, scatter graph. Oh, there's my timer. It's time for lunch. Insert scatter graph. We want to add a title, axes, trend line, and display the equation. So title, reasonable title could be period versus square root length. We click the plus, add axis titles. On our x-axis was square root length, and that is in meters to the power of a half. And to get superscript, I hit Control Shift plus. Meters to the power of a half. Period, measured in seconds. We add trend line, more options. Hit the trend line options tab. So linear, automatic's fine, display equation. And of course, like before, you can, increase the font size, maybe even make it blue to match the trend line. And even type directly in here. So t equals square root of L. So instead of y and x, right, in physics we need to be specific, time period, and not length, but square root length. Click the graph, copy, take it over to your report, and paste it in. Make sure it's nice and big. Well, actually, yeah, our next step will be adding to this graph, so you can hold off on this step until then. But my timer went, and I need to eat my lunch, so you have a break too. And then next up, we will be adding error bars, calculating line of steepest fit, and finally the conclusion. And we're there. All right, I'll see you then.